Hi and welcome back. This is video 1 of 2 on Chapter 16. Chapter 16 introduces us to the idea of the electromagnetic wave, which we know as light. Now, to get there, what I'd like to do is to introduce you to two theorems that we've actually seen previously. They're math laws, or theorems. And the first one is Gauss's law. Now, we use Gauss's law extensively when we talked about the electric field. We did use it once with respect to the magnetic field, just to show you one of the results that leads us to the conclusion that the magnetic field always loops back onto itself. But Gauss's law says the following. If you were to integrate a field, which I'll call A, if you were to integrate, rather, the divergence of a field, which I'll call A, over a volume, this is the same as looking at that field as it passes through the surface, the closed surface of that volume that bounds it. So this is Gauss's law. And then there's a theorem called Stokes' theorem, which says the following. If I were to look at the curl of a field, in a surface, that is the same thing as that field integrated over a closed loop. Stokes' theorem and Gauss's law. Now, when it comes to defining the properties of the field, there are only two things that you need. You need to know the divergence of the field, and you need to know the curl of the field. So, both the divergence and the curl are examples of differential things. That's what we call them. And so these are the differential forms of these equations, you could say. Now, that said, if you go back and you look at some of the most important equations that we talked about with respect to magnetism and electricity, they are the following. One of them came from Gauss's law, which said that if you look at the electric field as it passes through a closed surface, that's the same thing as Q over epsilon naught. I'm going to call this number 1. Another one, which I'll call number 2, talked about the behavior of the magnetic field. That is, if you were to look at the magnetic field integrated over a closed surface, you get 0. The third one was in relationship to the magnetic field again. And it said that if you looked at the magnetic field over a closed loop, you get mu naught times I. And the fourth one was Faraday's law, which said that if you looked at the EMF around a closed loop, it is d magnetic flux over time. Now, what I'm going to do is to take Gauss's law and Stokes' theorem and use them to take these 4 equations and put them into a form that's going to be a little bit more useful to us, at least theoretically or qualitatively. And I'm going to start with number 1. So with number 1, what I'd like to point out is that the amount of charge in a volume is what you get when you take the density of that charge and you integrate it over the volume, like that. So if I took number 1 and I rewrote the right-hand side the following way. It would look like this. Now I'm going to apply Gauss's law to the left-hand side. I have a loop over a closed surface, which is the same thing as the divergence, del dot, of that vector. Now we know from our discussion about Gauss's law that the volume and the area refer to the same thing. So these volumes are the same thing. What I'm going to do is to pull this right hand over to the left hand side and pull things up under the integrand, or up under the integral, if you will, rather. So I have a del dot E minus rho over epsilon naught dV is equal to 0. Now the only way that this could equal to 0 would be if this is equal to 0. So one way that we can write our first equation here is the following. Del dot E is equal to rho over epsilon naught. Okay? So I'm going to box this because we're going to need this in a little bit. Now let's talk about the second equation. The second equation deals with the behavior of the magnetic field when you look at how it enters and exits a volume. Basically what this says is that for each field that goes into a bound surface, it's going to be equal to a vector that exits, giving you 0 overall. So if I were to take this right here and use Gauss's law on it, this is the same thing as saying del dot B over a volume is equal to 0. And again, making the same argument over here, the only way that this could always be true would be if del dot B is equal to 0 itself. Right there. Now, the third one, what I'd like to point out for that one is similar to what I pointed out with respect to the charge, the relationship between charge rather and charge density, is that current can be related to current density. So it's generally written the following way. Because we know current density is current per unit area, and we've used this in previous chapters. So what I'll do is to use this in conjunction with our third equation over here. And if you look at this, it says B dot dl is equal to mu naught times I, which would be mu naught times J dot n hat ds. Now I want to use Stokes' theorem. Stokes' theorem says that anytime you have a situation where you're integrating a vector over a closed loop, dot dl, you can write it as a cross product. So on the left hand side over here, I can write this as del cross B dot n hat ds, and here I have a mu naught j dot n hat ds. I can pull these under the same integral, move this to the right hand, or to the left hand side rather, and that would be del cross B minus mu naught j dot n hat ds is equal to 0. The only way that this is consistently 0 would be if this right here is equal to 0, which means that I have del cross B is equal to mu naught j. This is another one that I'm going to box. So we have 1, 2, 3 differential forms of our equations here. Now let's work on number 4. Now, number 4 says the following. If you look at the EMF um, that's generated by the changing magnetic flux over time, it looks like this. Now, EMF is voltage. You can think of this as the integral of E dot dl, but this is over a closed loop, and the reason why it's over a closed loop is because in order for our EMF to do anything, to move current, for example, there needs to be an unbroken path, an unbroken loop, so it's a closed loop. On the right-hand side, I have the magnetic flux. The magnetic flux is equal to B dot n hat ds, right there. And so what I'm going to do is to take and use Stokes' theorem on this. Stokes' theorem says if you were to look at this equation right here, let me just write it out. Okay, so this is the left and the right-hand side. That this right here, I could write as del cross E dot n hat ds. And so I can pull the right-hand side over to the left-hand side in exactly the same manner as I've been doing so far. And when I do that, I have a del cross E plus a dB dt, noting the fact that the surface here isn't changing with respect to time in general. It's something that we draw, we define. And again, this only makes sense if this is equal to 0. So we have del cross E is equal to minus dB dt. Okay, so again, you can box this. So for the 4 equations that I wrote down, that we've talked about extensively in the last several chapters, what I have are these 4 differential forms of them. So let me write them down over here, and then I want to talk a little bit about them. Specifically, I want to talk about one of them. So I have a del dot E is equal to mu over epsilon naught. I have a del cross E is equal to minus dB dt. I have a del dot B is equal to 0. And then I have a del cross B is equal to mu naught J. Now, let's talk about what's going on over here on the left-hand side. So I want you to think of a situation where you have a capacitor. Maybe your circuit looks something like this. You have a battery with a switch hooked to a capacitor, back to the battery, like this. And what you do is you shut the switch and you let the capacitor charge. Now, as the capacitor charges, there is a current flowing, through the circuit that's a function of time. Okay? So what I like to do, just momentarily, is to look at Faraday's law. Specifically, let's see, do I want to look at Faraday's law? Actually, no. I want to look at Ampere's law, but I want to look at this version right here. We're going to use the integral version for a moment. Now, so let's not forget what Ampere's law here says. It says that if I pick a surface, a closed surface, or not a closed surface rather, but a surface that has closed edges, and I integrate along a closed loop on that, just the perimeter of that surface that I pick, that's going to equal to, okay, let's back up. Okay, so um, what I'd like to do now is to take those four equations and write them here, and then I want to talk about one of them. I want to talk specifically about the integral version of Ampere's law. In fact, let me start with that to begin with. So the integral version of Ampere's law says that if you take and you pick a closed shape somewhere, a loop, and that loop contains current flowing through it, I should get mu naught times I. Now the left-hand side is completely arbitrary. I just pick my loop where I know where the magnetic field is. And on the right-hand side, I should be able to talk about the current that is contained within that. So, that said, I'd also like to remind you about the right-hand side with current being equal to J dot n hat ds. Okay? Now J is the amount of current that flows through the surface that bounds my loop. Now watch. You see C1 right here? This is the curve. This is the integral that I'd like to look at. And here we have current, I'll say, is flowing this way. So if I were to take and put my thumb in the direction of the current flow there, what I would have would be a magnetic field that loops around in this direction like this. And sure enough, if I pick this closed surface right here, or this closed loop right here, on the left-hand side, I'd have B times 2 pi times r, since that's a loop. And on the right-hand side, I'd have mu naught times I, and you'd get the result that you expect whenever you take and you look at the magnetic field due to a long straight wire carrying current, mu naught I over 2 pi r. Now, watch this. What if instead of picking this surface right here, what if I pick this surface right here, this cylinder? Now, I still have the same curve. It's still bounded here, this open surface by C1. So this is the one I'm picking, but this is the surface I'm looking at. Will you agree with me that there's no current that's passing through this? But there's current passing through this. But this right here is my bound surface right here. So when I do the same curve, but I look at this surface right here, the right-hand side is equal to 0 because there's no current flowing through it. There's current flowing through this. There's no current flowing through this. We have a contradiction. Now, this is one of the things that James Clerk Maxwell pointed out. He said, look, if you look at all four of these equations, they're very, very useful, but there are contradictions within. Primarily, it's the contradiction that you see lies within Ampere's law, this one right here. Now, his solution was to say, okay, well, what we're going to do is we're going to put something called a displacement current. It's a fake current. We're just going to pretend that's there. And what that does is to allow this equation to sort of balance out and to allow us to get the same result if we were to use the surface right here as opposed to this. But in this surface, what's changing? Well, look at this electric field over here. So what he does is he defines this displacement current stuff. And it's defined such that if you were to put it in, it would look like this. Right there. So this was his big fix to these four equations. And as a consequence, he was able to write down four equations that connected electric fields to magnetic fields. Del dot E is equal to rho over epsilon naught. Del cross B, or del cross E rather, is equal to minus dB dt. Del dot B is equal to 0. And del cross B is equal to mu naught J plus mu naught epsilon naught dE dt. Now this isn't magic. In truth, this actually comes in part from something called conservation of charge. Through a equation that you see not just in electricity and magnetism, but in other places, dealing with different conserved quantities. That's called the continuity equation. So let me explain to you how you can look at these equations and get a feel for them. They actually mean things. So what this equation right here says is the following. Charge is the origin of the electric field. Electric fields come from or terminate into charges. That's what divergence tells us. This equation says magnetic fields do not have sources or sinks. There is no one origin of a magnetic field. With electric fields, there is. For example, you can have positive charges, which are sources of electric fields, that is, they come out of. You can have negative charges, which are sinks to electric fields, that is, they go into. But with magnetic fields, you find no one source or sink. This one says rotating or curling electric fields are caused by magnetic fields that change with respect to time. This says that rotating magnetic fields are caused by flowing charge or electric fields that change with respect to time. So there's a duality between the magnetic field and the electric field. Changing magnetic fields with respect to time can create electric fields that loop. Changing electric fields with respect to time can create magnetic fields that loop. Now it turns out that the electric field and the magnetic field are basically the same thing. To make my point, I want you to imagine a whole bunch of charges that are side by side, packed together like this. Now, were these charges stationary? When you observe them, you would see the electric field due to a line of charge. But if I were to take these charges and move them like this, now you would see flowing charge, current, and as a consequence, thanks to the Biot-Savart law, you know that you would see a magnetic field that loops around them. If they're stationary, you see an electric field that points straight out radially. If they're moving, you see a magnetic field that loops around them. Well, here's the deal. Motion's relative. What I mean is the following. Let's pretend that you are driving down the interstate doing 70, and there's a car in front of you doing 65, and it's really far in front. Now, as you drive down the road towards this car, you'll notice that it's slowly coming towards you. And that's because it's going 5 miles an hour less than you are. Now, the only reason why you know that you're moving is because you can look out of your window and you can see the road. You're moving with respect to the road. And the same is true for the car that's in front of you. But what if you took away everything that told you that you were moving? And let's just, for the sake of argument, pretend that you're traveling at a constant velocity. Well, if you take away the road, that says that you're moving. If you take away your speedometer, you take away everything around you that's moving with respect to you. What you see is a void of space and a car very far away in front of you that is slowly moving towards you. You have no sense that you're moving. So in one scenario, you can think of as yourself moving towards the car that's in front because you're moving faster than it. But in another scenario, you can think of yourself at rest and that other car moving towards you. Mathematically, they're both exactly the same. You get the same answers if you do physics with them. That's the reason why we say, from way back in University of Physics 1, that there are no experiments that you can do in an inertial frame of reference that tell you that you are moving with respect to something else. Now, so if I were to take this line of charges and move them, or if I were to move with respect to the line of charges and they were stationary, I'll see exactly the same answer. I'll see a magnetic field. And what that says is that the difference between the magnetic field and the electric field is that one is seen under motion and one is not. Now, they're the same field. So here, the duality here makes sense. Now, not only that, I'm going to tell you about this. I'm not going to do it because it requires Calc 3 and greater levels of calculus. But you can take, for example, this equation here that relates the electric field to the magnetic field, and you can combine it with, say, this equation right here, which relates the magnetic field to the electric field. And at the end of the day, you can get an equation that is an equation that we have seen in physics for a very long time, that we understand very well, and it's the wave equation. Now, if I were to look at just one dimension of this, I'll use the y direction. If you do it, you'll get an equation that looks like this. This is the wave equation. This is a very well understood equation. If you were to go back and look at the very beginning of the semester where I talk about waves, you'll see a derivation of this equation rather. And sitting out in front of the wave equation, in front of the time term, usually is 1 over the speed of the wave squared. Conventionally, we use the letter c for speed. And so what you have here is 1 over c squared would equal to mu naught times epsilon naught. So if I solve for c, it's 1 over the square root of mu naught times epsilon naught. And if you solve for this, you end up with a number that's about 3 times 10 to the 8th meters per second. This is the speed of light. What we have done through the Maxwell equations is come up with a joined electric and magnetic field that travels like a wave outwards and has the speed that would be the speed of light. This wave is called the electromagnetic wave. So one of the things that it requires, if you were to look at this equation right here, is a changing field with respect to time. And looking at this equation here, or looking at this equation here, the only way that you get this is if you have a current or something else that changes with respect to time that's generating your field. So I want you to imagine a current running through a wire that's changing with respect to time. maybe it's changing this way with respect to time. You take and you put your thumb in the direction of I and curl your fingers around it, and the curl of your fingers tells you the direction of the magnetic field that's created. Now this magnetic field right here changes with respect to time. If I go over here and look at my equations right here, a changing magnetic field with respect to time creates a circulating electric field. So here's your circulating electric field. But if this is changing with respect to time, this is changing with respect to time as well. And if the electric field is changing with respect to time, that means that you create a circulating magnetic field. A circulating magnetic field that changes with respect to time creates an electric field that changes with respect to time, that creates a magnetic field that changes with respect to time, which creates an electric field that changes with respect to time, which creates a magnetic field which changes with respect to time, and voila, you have a wave that radiates outwards. Now here's the deal though. The magnetic field itself is perpendicular to E. Okay, they're at right angles to each other. But when you look at the properties of them, there's a clear relationship between E, B, and the direction of the travel of your wave. Now we call the direction, K, the wave number. And the relationship here is that E cross B is in the same direction as K. Now, there's actually another relationship that we'll be talking about momentarily that's called the Poynting vector, which we'll get to here in a little bit. I want to talk more about the wave nature of this to begin with. And that said, this is a wave, which means that the relationship between C, lambda, and F that we got way back when at the beginning of the semester still holds here. The speed of your wave is equal to lambda times F. Now what about lambda and F? Well, take a look here. So, our eyes are designed very loosely to perceive colors that lie between blue or purple and red. Okay, so this is the visual range of light. It sits between 700 nanometers and 400 nanometers, but light itself is far more than what you can see. Now, if you go this way with respect to wavelength, where it gets bigger and bigger and bigger and bigger and bigger, from the visual range, the next gap of well understood light is in the infrared. Now there's a very small gap after infrared that would be microwave. Probably better suited to about here maybe. And then beyond that you have radio waves, and then when you get over here we usually say it's long wavelength. Radio. Now on the other hand, if you go the other way towards shorter wavelength, you have ultraviolet, you have X-rays, and then you have gamma rays, which are the most energetic forms of light that we're aware of. Now look, lambda times F is equal to C. And in all of these waves right here, unlike mechanical waves, all of these waves have the same speed. In a vacuum, it's 3 times 10 to the 8th meters per second. So, if I were to make lambda big, and the right-hand side stayed constant, F would have to change and get smaller. So the longer the distance between peaks, the less frequently you see the peaks. So what that means is that this might be in the direction of long wavelength, but this right here would be in the direction of long frequency, or big frequency, or high frequency. The shorter the wavelength, the smaller the wavelength, the more frequently you're going to see the peaks. Okay? Now, just as a simple example, what's the frequency of red light that has a wavelength of 650 nanometers? So, first of all, we're going to assume that this is in a vacuum. The speed of light in a vacuum is 3 times 10 to the 8th meters per second. Now, what happens if you're not in a vacuum? Well, the electric field and the magnetic field part of your light interact with material, and what that has a tendency to do is to bend it. So it makes the path that your light has to travel to get from point A to point B longer because it bends it. What that does is to make the speed less. But if you were to look at the instantaneous speed, at any time along the path, you'd still get 3 times 10 to the 8th meters per second. Now, our wavelength here is 650 nanometers. Now, that is times 10 to the minus ninth meters. Okay? And what we're trying to find here is F. So C is equal to lambda times F. F is equal to C over lambda. That's 3 times 10 to the 8th meters per second divided by 650 times 10 to the minus ninth meters. And when you put that in your calculator, times 10 to the 8th is divided by 650 times 10 to the minus ninth. You get 4.61, or 62 rather, times 10 to the 14th. Now, so one of the big conclusions that you should draw from this is that light really is nothing more than a combination of electric and magnetic waves. But in order to produce this, or electric and magnetic fields rather, but in order to produce this wave, you have to have some sort of changing current with respect to time. Now, there are other ways to produce it as well. We're not going to talk about those in this course. If you're more interested in things like that, what I would do would be to take possibly a modern physics class or an astronomy class where they go into the creation of light in great detail. Now, that said, what I would like to do now is to talk about the energy that's inside that light. Okay? So, if you remember our conversation a long time ago about capacitors, I talked about the energy density. That is the energy per unit volume between the plates of a parallel plate capacitor. It was 1/2 epsilon naught times E squared. Now recently, when we talked about the magnetic field and where it stores its energy, in say an inductor, that was 1/2 mu naught times B squared. Now, one of the consequences of solving this equation right here is that you get a relationship between the electric field and the magnetic field. And that relationship is the following. The strength of your magnetic field in light is equal to the strength of the electric field divided by C. Okay? So what that means is I could look at the total energy density in light as being a combination of what's in the electric field and what's in the magnetic field. But when I do that, I have to acknowledge the fact that the electric field and the magnetic field are two sides to the same coin. Now, the electric field is a lot easier to deal with in general than the magnetic field, and that's because magnetic fields always loop back onto themselves. So usually what we do is we write magnetic fields in terms of electric fields, knowing that we can get to them through this relationship if we need the magnetic field. So here, what I'm going to do is to plug in B is equal to E over C into this. Now when I do that, I have 2 mu naught C squared here, and then I have my E squared there. But look, mu naught times epsilon naught is equal to 1 over c squared. So if I were to move, for example, mu naught over here, epsilon naught would be the same thing as 1 over mu naught times c squared. And I have a mu naught over c squared right there. So what that means is that the total energy density inside my light is 1/2 epsilon naught E squared plus 1/2 epsilon naught E squared, or just epsilon naught E squared. Okay, so that said, now what I'd like to do is to think about this energy density. It's the amount of energy per unit volume. Here's your light traveling through space. And what I'd like to do is to sort of think of I don't know, like a little cylinder, a little cylindrical chunk of volume that this light's passing through. So here's my little chunk of volume that is passing through right here. Like that. Whoops. It has an area. It hits this, travels through it. Okay. So this distance right here, which I'll call dx, is the same thing as, c times dt is traveling at the speed of c. Okay. So the total volume here inside my my little cylinder right here would be the area times the length, and the length would be dx. We'll call this dv. Like that. Okay. Now, so this is my energy density right there. My volume here overall would just be A times C times T, if you want to think of it like that. The total amount of energy trapped inside my volume right here would be you write it a little bit better like this. I'll call it du. Would be equal to u times dv. Epsilon naught E squared times A times C times dt. The power would be du dt, or, let me just make my life a little bit easier this way. Like this. The dt's cancel. The intensity would be power over area, or just u times c. There you go. That is the intensity of the light in this relationship to the energy density. Now, why is this a big deal? Well, the first thing I'd like to point out is that U itself depends upon E, and E, it's going to be a position, it's going to be a function of position, and it's going to be a function of time. Now, how do I know that? Well, when you actually solve your equation here, when you solve your equation for E, you're going to get an EY that looks like E naught times cosine of kx minus omega times t. This is called a plane wave solution. Now we're not going to go into any great detail here. This is a very well understood thing. It does require, for good understanding, a more complex understanding of physics as well. K and omega are both related to lambda and F. Through methods that you're somewhat familiar with. K is equal to 2 pi over lambda. Omega is equal to 2 pi over t, or just 2 pi times f, as we talked about actually in previous videos very recently. So, there is a time dependence to this, which, we kind of hand waved a little bit through when we were doing this derivation. Technically, your power, this would be an average power. You would get to this the same way. It is a little vague whenever you take and do the differential of this, but that's okay. This is a very back of the envelope calculation if you want to look at it like that. Now that said, there is this thing which I'm going to write down. I'm going to tell you why it looks the way it does. It's called the Poynting vector. Deriving it, unfortunately, does require a much higher level of math than what we have to work with right now. But the way you can visualize it is that it's the flow of energy, specifically the flow of intensity in a particular direction. Now, k vector is the wave number. It goes in the direction that your light travels. K hat here is in the same direction, but it's a unit vector. K hat would be the same thing as k vector divided by its length, which, in calculus you should have seen if you're in vector calculus at all. So the relationship here in terms of electric fields and magnetic fields looks like this. This is the Poynting vector. Written like this, generally used like this. This is how, when I wrote this right here down, and I talked about the relationship between E and B and K, this is where that relationship comes from, is through the Poynting vector. Now, that said, I just wanted to point that out, just for completion. But what I would like to do is to talk about a more useful version of intensity. And that is the intensity that you get when you get rid of the time dependence. So what we're going to do is to average our intensity over time. Now, the fundamental theorem of calculus says the following. If I want the average of a mathematical function, which I'll call that right there, or sometimes to show a time average, if f is a function of x and t, they'll write it like this. It is the integral from a to b of your function over whatever it is you're integrating times 1 over b minus a. This is the fundamental theorem of calculus. This is an average. So this is how you average out, for example, time in this case. So the electric field E itself, like I said, it has a constant part, E naught, and then you have this wave part, which is going to be k times x minus omega times t. And what I'd like to do is to average our electric field, specifically our electric field squared, so we can come up with an average intensity, I. Now we're going to do this over one period. It oscillates with respect to a frequency of omega. Omega is 2 pi over t. T is the period. So I'm going to average this over one period from 0 to t. Just like that. Now what's our I equal to? Well, I itself, we know from our conversation back over here, is just the energy density times C. And the energy density we discovered was epsilon naught times E squared over C. Okay? So when I put this into this equation right here, I have an epsilon naught over T times C. Okay? And now I'm integrating my electric field, which is a function of position and time, potentially, from 0 to 1 period over time to get rid of the time part. Now let's talk about the electric field. Like I said, E itself is going to look like, as a vector, E naught times cosine of k times x minus omega t. To get E squared, you dot it with itself, which gives you the magnitude squared times cosine squared of kx minus omega t. Now, what I'm going to do before I take and I put this back in our integrand and I integrate this is to massage this a little bit, specifically looking at the trig part, cosine squared of kx minus omega t. I can get from a squared cosine to a cosine that's not squared using the following trig rule. That one right there. And so this is the same thing as 1 plus cosine of 2 times kx minus omega t divided by 2. So what that means is that my intensity here, on average, is going to be epsilon naught over T times C. So that takes care of the leading stuff right here. I have an E naught squared. And then I'm integrating from 0 to T 1/2 plus 1/2 cosine of 2 times kx minus omega t dt. The first thing is very easy to integrate, this first term. When I do that, the first term is just going to be 1/2 t. But I still have this integral right here to do. So let's take a look at that. This is just this integral right here, just this part. This is what I want to integrate. Now, here, I'm going to use another trig rule, and that's that cosine of a plus b is equal to cosine a, cosine b, minus sine a, sine b. So what that means is that I can write this particular integral the following way. It's actually two integrals from 0 to t. We'd have a cosine of 2kx cosine of 2 omega t. You might be wondering where the negative goes. Cosine's an even function. And then I have another one. When I plug in the negative, that's going to pull out, since this is an odd function, and make that positive. This would be a sine 2kx times sine of 2 omega t dt. Now I'm only going to do one of these integrals, and there's a reason for that. I'll do the first one just to sort of show you how this turns out. Cosine 2kx isn't a function of time. I can pull that out. I have my cosine 2 omega t right here. Well, the derivative of sine is cosine, so when I integrate this, I get a sine back. I need to do a substitution here, though. U is equal to 2 omega t. So du will be equal to 2 times omega times dt, which means that this would be the same thing as cosine of 2kx over 2 omega. My limits of integration here are going to go from 0, which when you take and you plug in 0 for t is 0. And we have, oh, hold on now, watch. So when I take and I plug in t here, remember this is one period, that would be 2 omega capital T. Omega itself is 2 pi over t. So when I plug that in, this is the same thing as 4 pi. Okay, so that's my limit of integration right there on the top's 4 pi. Now it's cosine of u du. I integrate this, I get a sine. At the end of the day, I'm evaluating sine. 4 pi at the top, 0 at the bottom, this is 0. That's 0. You get the same thing if you do this. You do this, now instead of a sine, it's a cosine that you're doing. Cosine of 4 pi is 1, cosine of 0 is 1, 1 minus 1 is 0. Anytime you average a periodic function over one period, like a cosine or a sine, you get 0. So what that means is that this integral right here, this is 0. Okay? Which means that it's this part that only matters. The t's cancel, which means that my average intensity here, I, is 1/2 epsilon naught times E naught squared. And that's that. Now, as an example, let's take a look at this. Right down the road, we have Magic 107. It's Orlando. It broadcasts with 98,000 watts of power. What I'd like to know is what's the intensity of this radio signal in DeLand, what's the intensity in Daytona Beach, and what's the peak magnitude of the electric field and the magnetic field in Daytona Beach. Now, to do this, we need a little bit of information. Let's write down what we've been given here. The power due to this broadcast is 98,000 watts. I'd like to know the distance to the land. If you look it up, that ends up being about 66 kilometers, or 66,000 meters. The distance to Daytona Beach is about 90 kilometers, or 90,000 meters. Okay? What I'd like to find is the intensity in DeLand, the intensity in Daytona Beach, and also E naught and B naught in Daytona Beach. Okay? Now, the way to do this is to think of your transmitting tower as putting out a wave that's centered on itself is spherical. And this thing travels outwards like that. Okay? Travels out in all directions. Now, intensity itself is power over area. And if you think about what the area of a sphere is, well, the area of a sphere is 4 pi r squared. Which means that if I want to find the intensity in DeLand, what I need to know is the power that this transmitter has. And I also need to know how far away from the transmitter I am. And I know that. So for that, that would be 98,000 watts divided by 4 pi times 66,000, whoops, meters squared. What am I doing? Meters squared. That's better. Okay, so 98,000 divided by 4 times pi times 66,000 squared. That's an intensity of something like 1.79 times 10 to the minus 6 watts for every square meter. Now what happens is if you think of your antenna in your car as being like this, there's your antenna. And here's your light wave coming in. The electric field part of the wave, when it hits, takes the free electrons that are inside there and shakes them back and forth with the same frequency that this broadcasting station does. Your radio is connected to this, and what it does is to look at that frequency that you've tuned to and look for variations around the frequency, because that's where the data that you would consider to be the music that you're listening to is carried. Now, we can do the same thing for Daytona Beach. In Daytona, the intensity in Daytona Beach is just going to be the power over 4 pi times the distance to Daytona Beach squared, or 98,000 watts divided by 4 pi times 90,000 meters squared. So when I take and I do this, I get 9.63 times 10 to the minus 7th watts per square meter. So that's the intensity at Daytona Beach and the intensity in DeLand. What about the magnetic field and the electric field? Well, look, we have relationships between intensity, electric fields, and magnetic fields. So right here, the intensity here on average is 1/2 epsilon naught times E squared. And we also know that the relationship between the electric field and the magnetic field looks like this. The electric field is equal to C times the magnetic field. So we have I in Daytona Beach, and really all we're doing is looking for E naught. E naught in magnitude would equal to 2 times I divided by epsilon naught, the square root of. Let's see, epsilon naught was it 8.85 times 10 to the minus 11th, I believe. Let me check here. It's the problem with being in magnetism for so long. 8.85 times 10 to the minus 12th. Coulomb squared per Newton meter squared, right? To the 1/2. All right, so let's see what we got there. Take this, multiply it by 2, divided by 8.85 times 10 to the minus 12th. And then I'm going to take the square root of that. And I get 466 newtons per coulomb. Now, if I want to know what the magnetic field is, I just take E and divide it by C. So B is going to equal to E naught, or B naught is equal to E naught divided by C, which is going to be 466 newtons per coulomb divided by 3 times 10 to the 8th meters per second. And you get 1.55 Tesla, 1.55 rather, times 10 to the minus 6 Tesla. So there you go. You got the magnetic field, you got the electric field, and we also have our intensities. Okay, so that's it for this video. In the next and the last video for this course, we're going to discuss radiation pressure, which is actually pretty cool. And I'll see you then.